Ah, okay. So the title is An Introduction to Conformal Prediction. Is it fine or should I rewrite it? But then later. Okay, thank you. Good point.
Bonjour à tous, bienvenue dans cette masterclass. Donc aujourd'hui on aura le plaisir d'écouter Sébastien Gerchinovitz, qui est chercheur à l'Institut de recherche technologique Saint-Exupéry à Paris et également chercheur associé à l'IMT, donc il va parler de introduction à la prédiction conforme. So, hello everybody, today we'll have the pleasure to listen to Sébastien Gerchinovitz, who is a researcher at the Institute for Technological Research Saint-Exupéry in Toulouse, and also associate researcher here at EMT, and he will speak about introduction to conformal prediction. Sébastien, please.
So thank you very much. So I'm very happy to have the opportunity to give you a course. So I heard that there were many different topics that you were meant to discover. So here is a statistics topic. Okay, it's a topic related to what we call statistical learning theory. So I won't assume any basic knowledge of statistical learning theory. Just give you some introduction to the topic. And for those who know some geometry, the conformal word has nothing to do about the geometry meaning. Okay, it's something different. You will see in a minute. So let's make some introduction. Okay, is it large enough? Okay, I can do like one letter per blackboard. Okay, so the context is the following. Just a few keywords, and then I will explain the keywords. So it's uncertainty quantification for supervised learning. So I will explain this in all the talk. So first let's start with supervised learning. So just a question, who has already used GPT, Gemini, things like that? Okay? So you are using things behind these keywords, okay? It's more complex, more complicated than just supervised learning, but it has to deal with this. So just in an informal definition, the goal is to learn a relationship, a function. Let's phrase it informally. From some x in some abstract set capital X to some y in some abstract set capital Y, using, so this, we call this the input. This, the y's, we will call them the labels. I will give a number of examples. And we will learn a relationship using a sequence of input label examples. So for example, if I give you 100,000 examples of images of plants with different plants on the images, then we want to learn using an algorithm and using this data, the relationship between the image and the name of a plant, okay? So what I told you is just a specific example of what is known as classification. So I'm just running through examples in an informal manner. Okay, I will get to the mathematical details a bit later. Classification. So if for the purpose of illustration, let's think of it as plant recognition. So who knows about the collaborative project or the app PlantNet? Who has already heard of that? Okay, so PlantNet falls within this topic, okay? So we have an image of, say, a flower. Okay, this is my best picture of a flower. So X is an image. And the goal is to predict Y, which is the name of a plant. And we want to learn this relationship using a set of examples with images that are annotated with humans who said, hey, this is this plant or this is this plant. So the goal is to find automatically patterns between what we have as inputs and what we want to know, which is the unknown label. So is that clear at this stage? Yes? Okay. So let's give another example. So this is the second, maybe simplest example, which is known as regression in statistics theory. So, and for illustration, I will describe a very specific example, which is known as magnetic declination prediction or estimation. So on the Earth's surface, you have a geomagnetic field, and you should be aware that the magnetic north does not coincide with the true north, right? It even varies over time. And if you are on a given location in the Earth's surface, there is some angle locally between the true north, the direction of the true north, and the direction of the magnetic north. So this angle is called magnetic declination. And knowing in an accurate manner the value of the magnetic declination is useful for some aeronautics uses, for example. And so in this case, we can have X, which is the latitude, the longitude, and the altitude, which I abbreviate like this. And the goal is to learn a relationship between, and maybe even the time, okay? And it's to learn a relationship between X and Y, which is the value of a magnetic declination. Again, if we collect some measurements at different places on Earth where we know the latitude, the longitude, and the altitude, and we measure the magnetic declination, maybe we can extrapolate from this data to learn the relationship, okay? So this is another example of supervised learning. Here we predict in a discrete space. In classification, here it's within a continuous space there. Let me finish with a third example. But there are multiple other examples. So object detection. Sorry. And if you want to think of a specific application domain, let's think of self-driving cars. Autonomous cars, so which are being developed currently. So again with a picture, so X is an image, and we have an unknown number of different objects of different types on the image. So let's say that we have some pedestrian there, and that we have a bicycle. So my best picture of a bicycle. Okay, not so bad. And so this is x. And I will draw y on the same image. So y is given by two rectangles, which are the smallest rectangles that enclose the two objects. And we want a name for these objects as well. So here we will write pedestrian. And we will write as well bicycle. So this is y, locations, and names of objects. Of course, you have to define what is an object, etc. Okay? So this is a bit in between these two examples because you have both a classification task and somewhat regression task as well, even if these are non-independent tasks and there is an unknown number of objects, so it's a more complicated task. And there are multiple other examples. And I will just make a short list. So what can I say? Image segmentation, for example. So for example, on an image, we want to find the very precise locations, not a rectangle, the very specific shape of a tumor on some MRI scan imagery, for example. We could want to do some weather forecasting. So to predict the state of the atmosphere in every possible place for every possible atmospheric variable, given some measurements and some current predictions, for example. Let's change topics. Protein structure prediction. So there has been, over the last, say, 5 years, even a bit more, huge progress into the problem of predicting the three-dimensional structure of a protein given the sequence of the amino acid sequence, which is a very complicated problem. And then every task pertaining to natural language processing, like machine translation, for example, which works pretty well now. So if you give your favorite LLM some text in English, the translation into another language will be pretty accurate, right? Okay. So these are examples of supervised learning problems, even if I didn't get into the details. And an important remark is that modern applications represent F, so the unknown relationship that we are trying to learn through what is called an artificial neural network. So F, I didn't define it, it's the unknown relationship that we are trying to learn, okay? Okay, I know I'm not, to detail every specific sub-problem, we would have to get an entire set of multiple hours probably. So I'm being a bit informal there. So this, I will write this A and N. So who already heard about neural networks? Okay, it's fine if you didn't because it will be mostly orthogonal to neural networks, what I will talk about later. But this is important for cultural reasons. So a large family of artificial neural networks can be written as a finite superposition of elementary functions like linear combinations, and some nonlinear activation functions. If you know the superposition theorem by Kolmogorov-Arnold, for example, to represent continuous functions of multiple variables or algebraic functions of multiple variables, this is the same type of structure that we have behind. So there is a big challenge there, is that, let's phrase it simply, great empirical results. So the last decade, even a bit more, has seen unprecedented performance results in these tasks using artificial neural networks. But artificial neural networks are known to fail. So maybe on some specific task, or on average, or 90% of the time they work well, but there are cases in which we know they fail, and there are cases in which we can't afford such failures, like tumor segmentation, for example, or object detection for self-driving cars, or even weather forecasting would be dramatic in some cases, okay? Are known to fail, so we need to quantify prediction errors So this is where the word uncertainty quantification comes in. So there are safety critical applications in computer vision, like I said, but also in the daily life. If you use your favorite LLM for any cognitive task, then you'd rather have it non be too much inaccurate, right? Okay. So the bad news is that there is a huge research effort. There has been a huge research effort in what we call deep learning theory, which is the mathematical theory for deep neural networks. But so far, theory lags behind practice. So mostly we understand some basic phenomena underlying neural networks, or we have very precise quantified error bands that are universal but way too conservative to explain the empirical performances, or much tighter bands but in very special cases. So far, if you take a huge number of such applications, deep learning theory is unable to explain or to predict the limitations, the failures, or the working conditions of artificial neural networks. It's very simplistic when I'm saying that. Okay? So problem, deep learning theory lags behind practice. Let's phrase it this way. And this is not a surprise, because deep learning theory is a combination of many different fields in mathematics. It involves approximation theory, harmonic analysis, algebraic geometry, non-smooth optimization, stochastic processes theory. You can put everything you wish. Game theory, optimal transport theory, and so on. So it's a very, very transdisciplinary problem within computer science and machine learning theory and mathematics theory. Sorry. So far we lag a bit behind practice. So today I wanted to talk about an alternative to such very complex theory, which is called conformal prediction, which does not help understand why neural networks work, but rather to properly quantify neural networks errors, even if we're a bit short of properly understanding why and how, okay? But then we can measure some errors and use such measurements in order, when using neural networks for a specific task, whether there is a chance that we're going to be correct or not, okay? So today I will talk about one method among the different variants of conformal prediction, which is called split conformal prediction. So which is much simpler, mathematically speaking, than deep results in deep learning theory, but which is applicable in practice, at least at the moment, compared to deep learning theoretical results. Okay. So I need some definition first. So the conformal word comes from this term, non-conformity score. It's just a function from y to y. Sorry, from y times y to the real line. And informally, sorry. So we will compare predictions of our function to the true label, and this measures somehow the difference or the error. So measures the error of predicting y with f of x. So let me look at the time. Okay. So I need to summarize a little. Okay. So let me give you just one example. Example 2, which is the simplest one in regression. So for example, here we would have s of f of x y, which would be just the absolute difference between the two. This is the simplest error function that you can define, right? So if you predict an angle and you want to compare it to another angle, then you just take the absolute difference, say. In classification, this is a bit more complex because everything lives in a discrete world, so you have to define a notion of error in a discrete world, but you can do it. In object detection as well, it's a combination of a discrete world and continuous world, but we can define notions of errors as well. So let's just take this example for today. And then I can now describe what is split conformal prediction. Okay, so split conformal prediction. It's a protocol, say, in 3 steps. So first, we learn F using some data. And this data, we call it training data. So this can be any machine learning machinery that you can think of. And for those in the room that are a bit more familiar with probability theory, when I write we treat F as fixed, it means that statements and proofs later that I will talk about are conditioned on this training sequence. Okay, so everything is conditioned. Probabilities are conditional to a sequence of training points. So we treat F as deterministic there. So now we collect some new data points. new examples. So n examples where the xi's are in x and the yi's are in y. I use capital letters because they will be random variables, okay? And we call this the calibration data as opposed to the training data. And the reason why there is the split word there is that we have some bunch of data, and some of which we allocated to train, to learn the relationship, and the remaining part we will use it to evaluate the errors of a function. While there are some more subtle ways to both train and evaluate through cross-validation procedures, for example, but these would be too complex to explain today. Okay, and evaluate so we evaluate the non-conformity scores for every example in the sequence. So we just realized that some predictions were correct, some of them were incorrect or in between. And we make a note of all of the values of all these errors, sorry. And then we pick a quantile. So then pick what we call an empirical quantile. So you might know the notion of quantile in statistics. Empirical quantile just means that we work on some empirical distribution, discretely supported distribution. So to do this, we order the values of the SIs. We sort them by increasing order. So the notation with the brackets there just means that this is the smallest one, the second smallest one, and so on. Okay? And the empirical quantile that we take, so given some alpha that you have to think of as a small real number, very close to 0. So we pick SK, maybe I should write it there, SK, where K is okay, so this is the ceiling part, not the integer part, the ceiling part, okay? And if you just get rid of the ceiling part and the plus one there, this would be the 1 minus alpha smallest one, okay? Among the n examples, here there is a small correction with a plus one there and a ceiling part, okay? So basically, I look at a fraction of 1 minus alpha in these values, and I take the 1 just in the end. And this is the value of SK, okay? So if alpha is pretty small, you have to look at a rather extreme value of S. And then third step, for any new not seen yet input X, we output a set C of x, which is the set of all labels that are close enough to f of x. And by close enough, I mean, oh, sorry, and I need this. And by close enough, I mean whose distance in some very informal way to f of x is at most of sk, the value that we just computed before. Okay? So put differently, we have or to summarize, we have a relationship that we learned in step 1, and we measure how close is it to the real value yi. Let's say it's the absolute difference in the regression case. When I see a new input x, I don't trust the prediction f of x, but I'm confident enough in that the true value of y will be just as close to f as the yi's that I've seen before were close to their predictions f of xi, up to some error margin, which I take as this, sk. Okay? So there are different choices for this uncertainty parameter, and these different choices lead to different theoretical guarantees. So this one is the simplest one, and it's the simplest theoretical guarantee, but there are variations around that. So if you want to take some extra margin, then that might enable you to get some extra guarantee as well. Okay. So importantly, instead of predicting a value in y, we now predict a subset of capital Y. Okay? So we now directly predict the uncertainty in some sense. So in regression, example 2 again, with this definition of S, C of x is equal to f of x minus sk, and f of x plus sk. So it means that instead of predicting a single real number, we predict an interval. And in other learning tasks that are more complex, you can somehow generalize this notion of predicting an interval instead of a single real value. Okay? So are there questions so far before I state the theorem? It's the moment. It's okay? Is it clear enough? Okay. So this is a theorem that we generally attribute to these people. So Papadopoulos et al. 2002, and Vovk et al. 2005. And I said usually attribute because if you look back in the literature, there were some very similar arguments in the 1940s, for example, but for slightly different algorithmic variants, even though these people contributed a lot to conformal prediction theory, not only to this very specific theorem. Okay, so there are some assumptions. So now are the probabilistic assumptions. So assume that the sequence of examples up to number n plus 1 So not only up to x1, y1, but I also consider an n+1 additional example on which I will formulate some probabilistic guarantee. You will see in a minute. But for the moment, let's concentrate on the assumption. Let's assume that it is exchangeable. So does anyone know what is an exchangeable sequence of random variables? I guess no one, right? You can know. If you know, please tell me. Okay, so you know random variables. Yes? A sequence of random variables is said to be exchangeable if whenever you switch some of them with any possible permutation, the joint distribution of a sequence remains the same. Okay? So in particular, it means that the distribution of any random variable is the same, but it means more than that. You keep the same dependency structure somehow. So let me write it. Exchangeable means that for any permutation sigma, of the n+1 indices, the distribution, let's write it this way, the distribution of x sigma of I, y sigma of I, for I is 1 to n+1 does not depend on sigma, okay? It's the same as if I had the identity there. So sorry, I need this is equal to distrib of xi, yi, So like I said before, it means that if I look at the whole sequence of random variables and the joint distribution of these random variables, it remains the same. It is invariant to any permutation of these random variables. So an important example of this is when the random variables are IID. So it means independent and identically distributed. And in this case, the joint distribution is just a single distribution tensorized to the number of random variables, and then you can swap easily. Okay, so let's assume this. And let's also assume that alpha is in between 1/n+1 and 1. So it's a mild constraint on the value of alpha. I said that we have to think of alpha as being close to 0. Well, not too much. It depends on the number of points. Then the probability that yn+1 is within the set C of xn+1 is larger than or equal to 1 minus alpha. So there is a sort of a opposite direction in the theorem, but I won't state it today. Not opposite direction, but the other statement means that it is not much below 1 minus alpha in a reasonable number of cases. Okay, so are there any problems about understanding the statement of a theorem? Is that fine? Okay. So let's interpret it. From a practical viewpoint, this is a good news. We have collected some data up to a number n of data points, and xn+1 is a new data point. And we want to predict some label yn+1 that we don't know at the beginning. And if we if we follow this protocol, the split conformal prediction protocol, then in the end, we construct a set of possible labels. And what this probabilistic guarantee tells us is that it will contain the unknown label yn plus 1 with large enough probability. Okay? So there are multiple limitations behind, like it's a purely average guarantee. It's not conditioned on anything. There are some statistical assumptions that you can question. There is the split protocol that does not reuse the training data for calibration purposes. There are multiple limitations that I won't have time to get into the details of. But at least it tells you something about the unknown value that you are trying to predict compared to the set that we output at the end of a prediction protocol. So just a simple example in object detection, an analogy with this would be that we have a set of rectangles that do contain the true objects with large probability, for example. Okay? Okay, so what I like about this is that the proof is simple. Okay, just a symmetry, it's just using symmetry arguments. Okay, I think I was a bit ambitious about the abstract. But let's do the proof. So I'm not sure I will have a lot of time after the proof. We will see. Okay, so let's rewrite what we have within the probability. So let's work with this event. What does it mean for yn plus 1 to lie within C of x n plus 1? Well, by definition of C of x that we have here, so C of x is a set of y's such that some condition is satisfied. So it means that this condition is satisfied, right? So it means that S of f of x n plus 1 yn plus 1 is smaller than sk. Okay, I'm just interpreting the definition of C of x. Okay, so now we need some additional notation that will help us abstract the problem and realize that it's just a symmetry type setting. So here we call this Sn plus 1. Okay, just as we called the SIs for this. And this, to be more precise, we will name it Skn. So I need to define what is Skn. Skn is the kth smallest value in S1 Sn. And so it's the same as S bracket k, but now I realize that it depends on n. And especially if I now consider the set S1 Sn plus 1, I have to make a distinction between whether I take the kth smallest value within n values or within n plus 1 values, which can be equal for some of them. Okay? So here it's just a reformulation. This is equal, the sk is just skn. But now we can realize the following simple fact, that this condition is in fact equivalent to this other condition, So where I replaced skn with skn plus 1. So this means that here we consider the n plus 1 real numbers S1 up to Sn plus 1. And the fact that Sn plus 1 is smaller than the k for them is in fact equivalent to the fact that Sn plus 1 is smaller than the kth smallest value within the first n values of Si's. So maybe just a picture. So it's going to be a proof by picture. But it's just as easy. So all numbers lie on the real line. So here we have S1n. Here we have, let's for the sake of simplicity assume that these numbers are pairwise distinct. Okay. Here we have Sk minus 1 n, and then Skn, and then everything up to Snn. So far I only ordered these n values in increasing order. And the question is, when is Sn plus 1 smaller than the kth of them? The kth smallest of them, so this one. And we can distinguish three cases. So if whether Sn plus 1 is smaller than the k minus 1 smallest of them, whether Sn plus 1 falls within this interval, or whether Sn plus 1 falls within this interval. And you can check that in any of these three cases, either the two conditions are valid or the two conditions are invalid. Okay? This is a very simple exercise. So that we have an equivalence then. And now we can get back to the proof. So we wanted to control the probability that P of y n plus 1 lies within C of xn plus 1, which we said was equal to the probability that Sn plus 1 was smaller than or equal to Skn. And by the above lemma, this is equal to the probability that Sn plus 1 is smaller than or equal to Skn plus 1. And this is where symmetry comes in. So Skn plus 1, maybe we need to be a bit more specific to really understand what is happening there. So you can write it as a function of n plus 1 arguments. So so the function takes n plus 1 real numbers as inputs and returns the kth smallest of them. Okay, this is Skn plus 1. And because we made a statistical assumption on the data sequence, which was that the SIs were exchangeable, it means that within the probability I can swap any random variable Si with any random variable Sj, say. So here I will do this with Si and Sn plus 1. So here this is the lemma that I used. And now I'm using exchangeability. Where I swap Si and Sn plus 1. Okay? So this is by the exchangeability of assumption. So there is some symmetry in the problem that we are currently exploiting. And this is true for any I. Even n plus 1. Okay? And if this is true for anyone, then I can average these values and I get the same value. So in particular, this is equal to 1 divided by n plus 1 times the sum from 1 to n plus 1 of what I wrote before, because all these values are equal, so they are equal to their mean. Ah, sorry, maybe I missed a step. Sorry, I need to write something before. I need to use symmetry again, saying that in fact I can swap back these two values because this is permutation invariant. The kth smallest element within a number of real numbers does not depend on the order of these real numbers, right? So this is permutation invariant. So this is in fact equal to phi k of S1, Si, Sn plus 1. And then this is just Sk n plus 1 as we had before. And because this is true for every value of I, this is also equal to the average of these values, which are all equal. And now we're almost done. Because you know that the probability of some event is the expectation of the indicator function. I take the expectation out of a sum, okay? So now we have the indicator that Si is smaller than Sk n plus 1. And now we're just within the expectation, we are counting how many SIs are smaller than the k smallest of them. Well, at least k, right? Could be larger, but it's at least k, so it's larger than k divided by n plus 1. And if you remember from the very first blackboard, maybe, or the second one, k is equal to the ceiling part of n plus 1 times 1 minus alpha. So this is larger than or equal to 1 minus alpha. Okay? And if for some reason this is exactly equal to k, this, which is true if the SIs are almost surely pairwise distinct, for example. I mean, not for example, I mean, yes, this is a sufficient condition. Then you have that this is smaller than k divided by n plus 1 as well. So it's a nearly tight lower bound there. Okay. So are there some questions? Did you get the main ideas behind both the context, supervised learning, that we need to properly address through some quantification of errors, then the protocol, then the theorem, then the proof ideas? Is it okay? Okay. So I have like 4 minutes. Should I show you some illustration or should we stop? We can? Okay. So let's wait. Maybe I should. Perfect. So while we're waiting, maybe I can comment a little. So there are multiple works in conformal prediction because as such, this very simple method is not that useful for complex learning tasks. Because we need to take into account that the distribution will not be the same or not exactly the same, that it can slightly evolve over time, or maybe because what I did is essentially a one-dimensional theory. The scores S are univariate, while in practice we usually need more than one-dimensional scores, so there are extensions toward that more general setting as well. Okay. So in the few remaining minutes, sorry, maybe I should not speak while typing this. Okay, I wanted to just to show you a few examples in object detection. So I will just skip to very simple examples. So what we call object detection in an informal definition is a set of two tasks or three tasks. We have to identify objects of interest on an image, all of them and not more. So somehow this is a super task, and what does it mean? It means that we have to localize them with rectangles, and we have to classify them into object types that we call classes. So for example, here we have a couch, so we should draw a rectangle around it and name it a couch. And here we have a TV, so we should draw a rectangle around the TV and name it a TV, and so on. And there are different colors. The green are what a human annotator said was a true object. So in particular, the human person missed some objects. So there are some errors also in the data set. And there are some false positives as well, which means that the predictions of a model in red does not sometimes they don't correspond to anything, or they correspond to half of the object. So there are errors in the predictions of a model as well. Okay? And the purple is just a slightly larger rectangle than the red one. And this is the analogy of our C of X there. Okay? So yeah, the results I'm showing you are based on some very classical, what we call in machine learning literature, a benchmark. So it's a famous data set that people are applying their best prediction methods on. Okay, so this is called Microsoft Cocoa, and there are very easy images, there are very non-easy images. So it's really a mess in terms of object detection. And just to show you very quickly the type of model. So this is the f of x that I was mentioning in the beginning. So it takes as input an image, and then there are some, there is a directed acyclic graph there where level after level we compute linear combinations, take some nonlinear transformations of these linear combinations and so on. So this is called a convolutional neural network. And then there is some type of deep learning model that we call transformer. So this is a quite recent neural network architecture that has been a reason for strong empirical performances. And at the end of the story, so at the end, the f of x is some rather complex object. So it lives in something to the n. So n is the number of predicted objects, which is fixed here. And every predicted object is given by a rectangle, which you can describe by, say, the coordinates of the upper left and the lower right corners, for example. And it's also given by a probability vector, which tells you the confidence that the model has in that it is a pedestrian, or it is a dog, or it is a bicycle. So the model does not predict this is a dog, it predicts this is a dog with probability 0.2, this is a bicycle with probability 0.3, and so on. And we also have a confidence score, which is the overall confidence, quote, quote, It's not a human, it's just an artificial neural network, but the overall confidence that the model has in that the predicted object does correspond to a true object. So we take this raw prediction, and we learn how to construct a prediction set, C of x, that uses the uncertainty that the model encodes in order to predict something that is true most of the time. Okay? And just to show you one very simple example. So in object detection, we have several tasks at the same time. We need to locate objects. We need to classify them correctly. But if we only care about location, so the localization task, so here we change colors, sorry. So what is called the truth is what a human annotator said was the best rectangle around the car, which is not 100% correct, as you can see. Okay. Sometimes the human annotator misses some objects as well. And the raw object detection model outputs the rectangle in blue. And what we learned through our split conformal prediction method was which error margin we should add to all these blue boxes so that the slightly enlarged orange box rectangles contain the red rectangles most of the time. Okay? So we learned a sort of error margin between the blue and the orange, and depending on the value of alpha, if you care about being true most of the time or just half of the time, you won't take the same error margins. Okay. So I think I should stop there. There are multiple questions that can arise from such pictures, but that was for the sake of illustration.
Thank you very much. Other questions or remarks?
Yes.
Can you say a little detail about weather forecasting?
Weather forecasting?
I will say what is the input and what is the output?
Sorry, can you speak? Can you speak?
What is the input and what is the output of, in the model of weather forecasting?
Sorry, I missed the question. What is what?
What is the input?
The image? The input. Ah, okay, sorry. So I will talk about some papers that I know of. Okay, there are multiple learning problems in weather forecasting, but the ones I had in mind when mentioning weather forecasting were recent papers by DeepMind, but there are also competitive with similar performances teams in China, for example. So the problem is the following. So the input is some highly dimensional vector describing the state of the atmosphere. So state of the atmosphere means three-dimensional field. I mean, it depends on three coordinates, but the output is something like 80-dimensional. So you have a number of atmospheric variables that you want to describe anywhere on the surface and in the atmosphere. So this whole discretized field is the input at some time t, okay? And given this, the question is what will be the next state of the atmosphere? And by next, we can mean within 1 day or 2 days. And the papers that I have in mind are up to 10 days forecasts, okay? So you need to learn the relationship between the current state of the atmosphere and future states of the atmosphere. And so there has been a huge machine learning effort in trying to mimic physical models, because the basis of all this work are extremely precise, research expensive, computationally expensive physical models of the atmosphere. And if you need just one simulation, it takes a lot of time to carry out. And there has been a huge recent progress in mimicking physical models through artificial neural networks. So people have been trying to define relevant neural network architectures so that if we feed them with lots of past data, which are states of the atmosphere and next states of the atmosphere, for example, we learn the relationship, and when given a new example of state of the atmosphere, we can predict the next state of the atmosphere. And the main progress has been made over the past 5 years or so. So the strong achievements have been since 2020, 2021 somehow. And so it comes at a huge, what we call inference time benefit. So it means that the simulation time when given a new state of the atmosphere is orders of magnitude reduced. Okay, I'm not sure about the orders of magnitude, but it's reduced by much. But there is something hidden, which is that the cost of that is a huge training time, as we call it. So we need a lot amount of data and a lot amount of compute resources so as to learn the proper parameterization of the neural networks. But then if you want to deploy this quickly in catastrophic situations, then this might be very useful, because you don't need 1 hour to compute the simulation, but just a few minutes, for example. And the progress was not for short-term forecasting, but rather for mid-term forecasting, where the existing forecasting models from the ECMWF, it's the European Center for Mid-Term Weather Forecasts, were just as accurate as now this center also implements very accurate learning models as well. But when this DeepMind team provided the so-called GraphCast model, and it now has different variants, they could do just as well as classical physical models did, but in a much reduced inference time. So this was the main benefit. Yeah, so is it clearer? Okay. This is a very nice topic, because it combines physics and deep learning. It's a really nice topic. Yeah?
What is the relationship between supervised learning and AI that you mentioned at the beginning?
Okay. So AI is like a bag of words, a bag of many different things. So, when you were not born, AI meant something very different. Then when I was doing my PhD, what I've been talking about was called machine learning. Okay? And then some people rebranded it as AI. But it's not exactly rebranding, to be honest, because since I've been doing my PhD, there has been huge empirical progress in not machine learning in general, but deep learning in particular. And AI can mean several things depending on the level, the scale at which you look at. So it can be like any algorithmic way to learn some patterns or some relationships in the data. Either relationships for supervised learning, where you want to learn the relationship between some X and some Y, but it could be some unsupervised task, as we call them, like to learn some patterns in the data. So for example, text generation, generative AI, as you know it. It's not necessarily some supervised learning tasks that are there. Models just learn what are the most likely characters or words or sentences that follow the previous text, for example, or that would correspond to your prompt, for example. So there are different learning tasks as well. And AI is all of that, and in particular, it's deep learning. So I'm not sure about a formal definition of AI. Maybe you should check Wikipedia to get the whole thing. But to be more formal, what I talked about was supervised learning.
here.
Yeah.
But if you have other questions, you can ask after Sébastien. Okay, so thank you again.
My pleasure.